Welcome back to All About RX. Today, we're diving right into this explainer to demystify a totally fundamental concept, the steric effect. In organic chemistry, it's really not just about what atoms are present, but exactly how they are arranged in three-dimensional space. It's a fascinating puzzle that dictates exactly how chemical reactions happen, or, well, why they completely fail. Let's break it down.
Okay, here's our quick roadmap for today's session. First up, the definition. Then we'll look at the three types of steric effects, run through some high-yield examples, and wrap it all up with a quick summary.
All right, Section 1, the definition. What exactly is the steric effect?
So the really crucial thing to grasp here is that steric actually comes from the Greek word stereos, which means space. Atoms aren't just abstract little letters on a page. They take up real physical space. When atoms get forced into a supercrowded position because of the physical presence of surrounding substituents, their energy levels spike. This spatial congestion, that is the steric effect. It literally means molecules become higher in energy and start acting differently. They might react incredibly slowly, they might demand a very specific orientation, or honestly, they might just refuse to react at all. Moving right along to Section 2, the three types of non-bonding interactions.
We can basically group these interactions into three main buckets: hindrance, shielding, and attraction. This is going to be our main framework for understanding how molecules behave in 3D space. You can kind of think of these as the physical traffic laws for atoms trying to interact with each other.
Now, this brilliantly illustrates steric hindrance, which is for sure the most common concept you're going to see. A bulky molecule can literally play defense and block another molecule from reaching the reaction site. Look on the far left. With ethyl bromide, the nucleophilic attack is super easy. But if you replace those tiny hydrogen atoms with bulky CH3 groups, boom, you've created a massive physical roadblock. Notice how the attack on the terp butyl bromide is completely blocked. It's impossible. The space is just way too crowded. What's really wild here is seeing the exact transition state where this molecular crowding actually happens. In an SN2 mechanism, the nucleophile has to physically reach that electrophilic carbon. When you just have small hydrogen substituents, there's practically no steric repulsion, so the SN2 reaction proceeds smoothly. But as you pump up that alkyl bulk, the steric repulsion gets so intense that the reaction mechanism physically shifts entirely away from SN2 and ends up favoring SN1 instead. Okay, our second type is steric shielding. This kicks in when a group is so massively large that it essentially protects a nearby reactive site. Take the highly unstable silicon-silicon double bond, for instance. It is naturally super prone to unwanted self-reaction. But here, these huge aryl groups act like massive molecular bodyguards for that sensitive Si-Si core. They successfully block identical molecules from getting anywhere close, while, surprisingly enough, letting tiny, nimble little molecules like oxygen or water slip right through the cracks to react. On the flip side of all that blocking, we have our third type, steric attraction. This happens when molecules approach each other and they have perfectly optimized complementary geometries. Because their shapes align so beautifully, temporary dipoles actually form between them. These dipoles then physically pull the molecules together, binding them in highly specific, locked-in orientations. It's almost like finding the perfect puzzle piece. All right, Section 3, let's look at the examples, specifically some high-yield molecular structures. Visualizing exactly how bulk changes a molecule is absolutely crucial for your exams. Let's look at the carbonyl carbons on the left. Formaldehyde has two small hydrogen atoms, right? So very low steric hindrance. But swap out just one of those tiny hydrogens for a bulky methyl group, and you drastically increase the spatial congestion to create acetaldehyde. We see the exact same thing playing out on the right side with amine nitrogens. Ammonia has really low hindrance, but trimethylamine, it's packed with three bulky methyl groups, giving it significantly greater steric hindrance. Finally, Section 4, the summary. Let's do a quick recall of our key takeaways. Before you wrap up this study session, here are your absolute must-know takeaways. Steric effects are all about spatial congestion, raising energy, whether that's steric hindrance, physically blocking a nucleophile, like a tertiary halide fiercely resisting an SN2 attack, or steric shielding, using those massive bulking groups to protect a sensitive core. Then there's steric attraction, pulling perfectly complementary shapes together. And please, never forget that classic mechanism shift. As alkyl bulk increases, that spatial crowding forces reactions to shift from SN2 over to SN1. To wrap up this explainer, I want to leave you with a pretty fascinating question. How could we deliberately manipulate these rules of spatial bulk and shielding to purposefully design the next generation of highly stable, targeted pharmaceutical drugs? Imagine literally utilizing those molecular bodyguards we talked about to protect a medication's active core until it reaches the exact right spot in the human body. That is the incredible, real-world power of mastering the Steric effect. If this helped your study session today, hit that like button and subscribe to AllAboutRx for more simplified pharmacy content. Keep that 3D space in mind next time you look at a molecular structure, and keep exploring.